Welcome to this explainer where we are going to completely dismantle the idea of a rigid body. You know, we usually think of objects like bridges, bones, and buildings as, well, completely immovable and solid. But because of the mechanical properties of solids, that's actually a total illusion. In reality, even the absolute strongest steel bar deforms under pressure. So today, we're going to explore exactly how and why that happens. We've got a pretty awesome journey mapped out today. We'll be covering 1. The illusion of solids, 2. Defining stress and strain, 3. The stress-strain curve, 4. The 3 elastic moduli, and finally, 5. Real-world extreme stress. All right, let's jump right in. Section 1. The illusion of solids. It is time to shatter that very first illusion, because, spoiler alert, perfectly rigid bodies simply do not exist. To really understand what solids do, we have to look at how they deform. On one extreme, you have elasticity. Think of stretching a standard helical spring. When you let it go, it completely regains its original shape and size, right? But on the flip side, we have plasticity. If you apply that exact same force to a lump of putty or mud, there's absolutely no tendency for it to regain its previous shape. It just gets permanently deformed. Most of the materials used in engineering, and honestly in nature too, sit somewhere between these two concepts. And knowing exactly how they behave is quite literally a matter of life and death when we're talking about building structures. Moving on to Section 2, defining stress and strain, the language of forces. To understand how materials behave under pressure, we first need to build up our vocabulary with these two fundamental concepts.
What's really fascinating here is the definition of stress. Because in physics, stress isn't what you do to the object. It's actually what the object does in response. When you push or pull on something, stress is the internal restoring force per unit area that's actively fighting back against your push. It's the material's way of trying to maintain its shape. Strain, on the other hand, well, that's the actual physical change in dimension that results from that stress. And depending on the direction of your force, stress and strain pair up in 3 main ways. First up, tensile or compressive stress alters the length of an object, creating what we call longitudinal strain. Second, shearing stress. That's a tangential force that physically twists or shifts the shape, creating shearing strain. And finally, hydraulic stress is when force is applied equally from all sides, kind of like being squeezed underwater, which compresses the volume, creating volume strain. Now that we've got our terms down, let's hit Section 3, the stress-strain curve. What's so interesting about this concept is that it acts as a literal map of a material's lifespan under pressure. It all kicks off with Hooke's law. Think of this as the golden rule for small deformations. For minor stretches and squeezes, the stress and strain increase perfectly in tandem, creating this nice linear relationship. Basically, you double the pull, the material doubles its stretch. Let go, and it bounces right back. Let's walk through a material's journey as we push it to the absolute limit. It bounces back happily at first in that proportional region, but if you keep pushing, it hits step 2, the yield point, or elastic limit. Push past that, and we enter step 3, plastic deformation. Even if you remove the load right now, the object is going to have a permanent set. It's never going back to its original shape. Finally, if you just keep adding strain, you inevitably hit step 4, the fracture point. That's where the material just completely snaps. Every piece of metal, wood, and concrete out there has its own unique curve, just like this. But you know, nature is full of exceptions. Just look at elastomers. Materials like rubber or the vital aorta tissue in your heart can stretch to several times their original length. They completely throw Hooke's law out the window for most of their stretch, and they don't even have a well-defined plastic region. They just stretch massively and snap back, which honestly is exactly what you want your heart vessels doing with every single beat. Let's move to the physical math in Section 4, the 3 elastic moduli. This is where we look at exactly how we calculate deformation. Within that safe, elastic region we were just talking about, we can calculate a material's ultimate fingerprint, its modulus of elasticity. This is essentially the ratio of stress to strain, and it tells you exactly how much force you need to achieve a very specific deformation. Because there are 3 types of stress, this modulus actually comes in 3 distinct flavors. The most famous of these is Young's modulus, which measures a material's resistance to changes in length. When you compare these materials, you can immediately see why we build skyscrapers the way we do. Steel just completely dwarfs aluminum and copper with a massive Young's modulus of 2.0 times 10 to the 11th newtons per square meter. It requires a staggering amount of force to stretch or compress steel even slightly, making it the absolute supreme choice for heavy-duty structural designs.
And when we shift our focus to the bulk modulus, which deals with volume and hydraulic compression, we find this mind-boggling contrast between the states of matter. Solids have incredibly tight bonds between atoms, making them highly incompressible. Gases, however, are about 1,000,000 times more compressible than solids.
Section 5. Real-world extreme stress. So the crucial point is how these abstract mathematical formulas actually play out in extreme, high-stakes environments.
Picture an incredible circus pyramid. Based on an actual calculation from our source text, the combined mass of the performers, tables, and plaques in this setup is 280 kilograms. The performer at the very bottom, lying on his back, is personally supporting 220 kilograms of that human weight right on his legs.
Mathematically, if we divide that weight across his two legs, that translates to a massive 1078 newtons of force bearing down on each individual thigh bone, or femur. I mean, that is an immense amount of compressive stress. But here's where the mechanics of solids totally save the day. Because human bone has a remarkably high Young's modulus, around 9.4 times 10 to the 9th newtons per square meter. That terrifying weight only compresses the performer's thigh bone by 4.55 times 10 to the negative 3 centimeters. That's a microscopic fraction of a single centimeter, a fractional decrease of just 0.0091%. Our bones are truly an absolute engineering marvel. Now let's plunge into another extreme. Let's travel 3,000 meters down into the deep, dark depths of the Indian Ocean. Down here, an object, and even the water itself, is facing intense hydraulic stress from the millions of gallons of water pressing from above. At this depth, the pressure is a crushing 30 million newtons per square meter. Yet, if we calculate the volume strain using water's bulk modulus, we find that the water at the bottom of the ocean is only compressed by a tiny 1.36%. So even under the immense weight of an entire ocean, water powerfully resists being squeezed into a smaller volume.
Which brings us to a final thought. We've seen that the rigid bodies we take for granted are actually dynamic, elastic systems. They are constantly fighting back against the forces around them. Knowing that nothing is perfectly rigid, how differently will you look at the bridges you cross, the buildings you enter, and even the bones in your own body today? They're all secretly flexing, stretching, and recovering all day, every day. Thanks for joining me on this explainer, and keep questioning the world around you.